In this lesson, we'll continue our discussion on learning target number 6, determining the empirical formula of an unknown compound, but this time we'll talk about getting it from using a CH analyzer or the formula of a hydrated compound. First, we'll talk about a carbon-hydrogen combustion analyzer, or a CH analyzer for short. It's a lab technique used to identify unknown hydrocarbon chemicals. So they mainly contain carbon and hydrogen, and sometimes can include oxygen, nitrogen, or a halogen. What we do is we set up a container where we're going to do a complete combustion reaction of the hydrocarbon. This will represent our balanced chemical equation, where we don't know what the ratio of C and H or any other elements in the original unknown compound. What we do is we burn our sample here in a glass tube and we pipe in pure oxygen gas to make sure that oxygen is not the limiting reactant, and we do indeed get a complete combustion. We have these pieces of glassware known as U-tubes attached, and the products from the combustion are forced through them. In the first U-tube, we have a chemical that likes to absorb water. To get experimental data, we detached the U-tube and we take the mass of it before and after we burn our unknown compound. The difference in those masses is the water that's created during the reaction. The same thing is done with this second U-tube, although we use a different chemical that absorbs carbon dioxide. Any other elements that are contained in the unknown sample don't get absorbed through either U-tube and exit with any unused oxygen. Since the only source of carbon and hydrogen is the unknown compound, we can use conversion factors or percent compositions to find the mass of carbon and hydrogen in the original sample. There are a couple of different mathematical ways that you can solve this problem. Figuring out the mass of C and H in the original compound is step 1 of the method we discussed in the last lesson. We can use the other 4 steps to find the empirical formula. Let's try out example 1. A 1.086 gram sample containing carbon and hydrogen is burned in a CH analyzer. 2.76 grams of carbon dioxide and 2.97 grams of water is produced, and we're asked to determine the empirical formula for the compound. I'm going to set up a little organizational chart for each piece of my formula. Now, the only number that I have to work with for the carbon is the 2.76 grams of CO2. And the only place where I'm going to get information about my hydrogen is from the water. And I've got 2.97 grams of water. Now, I haven't achieved step 1. This is not the grams of each piece of the formula. I need to somehow change the grams of CO2 into grams of carbon. The method that I like to use is by using the percent composition of carbon in CO2. Let's review how we would calculate that. What I would do is I would use the mass percent equation. The mass of the part divided by the whole times 100. So in CO2 there is 1 carbon, so the molar mass is 12.01 divided by the molar mass of CO2, which is 44.01, and if I times that by 100, the percent carbon is 27.3. I'll just use 3 sig digs on this. Now that I know the percent carbon, I'm going to use this information to change the grams of CO2 into grams of carbon. If I have 2.76 grams of CO2, then 27.3% of that is carbon. So if I times this by 27.3%, or in your calculator, you're going to times it by 0.273, that's going to calculate how much of that carbon dioxide was actually carbon. My calculator tells me it's 0.75348 grams. If you don't like that way to think about it, you could use your mass percent equals part over whole equation, sub in the percentage and the whole, and just rearrange for the mass of the part. I find timesing by the percentage is a little bit faster. For every CH analyzer question, the first step is the same. You can memorize that carbon dioxide is 27.3% carbon, then that way you don't have to recalculate it every time you do a question. If you forget on a test though, remember you can recalculate this by using the mass percent calculation. I'm now going to go through the same process and calculate the percent of hydrogen in water. There's 2 hydrogens in water, so I'm going to take 1.01, the molar mass of hydrogen, and times it by 2, and divide it by the mass of the whole, the molar mass of water, and times it by 100. Again, if I just use 3 sig digs, that's accurate enough for this type of question. So water is 11.2% hydrogen. I can use that information to change my grams of water into grams of hydrogen. That's how you achieve step 1 for a CH analyzer. I now have the grams of carbon and the grams of hydrogen, the grams of each piece of my formula. Step 2 is to change this into moles. I divide each of these by their molar masses. Step 3, set up a whole number ratio by dividing by the lowest value. That's going to be the carbon this time. This gives me a 1 to 5.24 ratio. I need to use step 4. That's too big to round. 0.24 is close to 0.25, which is a quarter, so I'm going to times by 4 to get whole numbers. Therefore, my empirical formula for this hydrocarbon equals C4H21. Let's try out example 2. This time my unknown sample contains carbon, hydrogen, and oxygen. It's burned in a CH analyzer, and the original mass of the sample is 2.524 grams. As products, I get 3.703 grams of CO2 and 1.514 grams of water. The first step of the CH analyzer question is just like what we did in the last example. I'm going to times the grams of CO2 by the percent mass of carbon in CO2. That will give me the grams of carbon in the original sample. I do the same thing for the water. I times it by the mass percent of hydrogen in water, which is 11.2%. To find the grams of oxygen, I need to figure out what mass was left in the original sample. I can't take the mass of CO2 times the percent of oxygen and add it to the mass of water times the percentage of oxygen in water. That's because in the original experiment, we pipe in pure oxygen to ensure that we have a complete combustion. Some of the oxygen from the CO2 came from the original sample, and some of it came from what we piped in extra. So to determine the mass of oxygen in the original sample, I take the mass before I burn the unknown, 2.524 grams, and I subtract the mass of the carbon and the mass of hydrogen that I just found. That's how you achieve step 1 if you have carbon, hydrogen, and another element. Step 2 in the process is to change each of these masses into moles by dividing by their respective molar masses. My oxygen is the lowest number. I set my ratio equal to 1 by dividing by it. This gives me 1 carbon, 2 hydrogens, and 1 oxygen. Therefore, my empirical formula equals C1H2O1.